Says recording has started. So today we'll start this topic. Subspaces. So one thing you need to understand with this subject is everything builds up on the previous work. So if you have not understood what we did previously, you will have trouble with subsequent topics. So it's important that anytime we cover a topic, you put in some effort and master the topic, the content before that, so that the rest of the topics will make sense. There is no, it's like a chain. Everything depends on what comes before. So with that in mind, I think we can proceed. So what we wish to do here is the following. Sometimes you have a subset of a vector space, which is also a vector space. So such a case, we say it's a subspace. We'll see some examples shortly. So it's basically a vector space that is sitting inside another vector space. We'll see some examples shortly. So now given a subset, you to check that it's a vector space, you have two options. One, you could check that it satisfies all the, I think there were 9 properties that we listed earlier, but it's not necessary to do that. It will be sufficient to show that it satisfies these 2 properties of vector addition and scalar multiplication, so that it's closed under those 2 operations. If you can show that the subset is closed under these 2 operations, an empty subset in that case, it's closed under these 2 operations, then we can confidently say that subset is a subspace. So not all subsets are subspaces. We are just interested in the ones that are subspaces. So what does it mean when we say closed under vector addition and scalar multiplication? So under vector addition, it simply means if you pick 2 vectors from the subset, add them, you still get another vector in the subset. And it's closed under scalar multiplication simply means if you multiply a vector by a scalar and the vector is from S, the resulting vector will still be in S. So if you can confirm that those 2 properties hold, then that subset is declared a subset. That subset can be called a subspace confidently. So there are some basic examples, the trivial examples of subspaces that we can use. One, if you have a vector space V, the set consisting of just the 0 vector and the whole space are considered subspaces. So the whole space is, from mathematics, you know that any set is its own subset. So you can think of the whole vector space as a subset of itself. And since it is also a vector space, we can call it a subspace. The set consisting of only 0 satisfies all the 9 properties because it's the only element. If you add 0 to itself, you get 0. If you multiply any scalar by 0, you still get 0. So it satisfies. You can check all the 9 properties, but it forms a vector space on its own. So these are the trivial examples. So there are some subsets which will definitely not be subspaces. We won't bother with those. If we have time, we can look at some just to make the point clearer. But our focus will just be on the subsets that are actually subspaces. So we'll start with an example. Here we pick a subset of R2 consisting of vectors whose first entry can be any real number and the second slot must be 0. So this is a subset of R2. So if you want to think of this graphically, this would be all the points that are on the x-axis, including the origin. So let's see what happens if you pick any two vectors from this set, from the x-axis in this case, and add them. What happens? So let's take the first vector to be this one, x1, 0. The second vector on the x-axis, x2, 0. If we add them, we still get another vector, x1 plus x2 in the first slot and 0 in the second slot. Since the second slot still has 0, it means this new vector is still on the x-axis. So addition of vectors on the x-axis still gives you another vector on the x-axis. So what's left is to check whether if you multiply a vector on the x-axis by a scalar, do you still get a vector on the x-axis? And if you can show that to be true, then we can claim that the x-axis is a subspace, or rather, if you like, vectors of this form a subset, which is a subspace. So let's check subspace of R2. I've skipped some slides. Yes, this was the next thing we needed to show. If you pick any vector from our set T, multiply it by a scalar, this is what you end up with. Again, it's still a vector on the x-axis, and we've shown it's closed with respect to vector addition and scalar multiplication. So we conclude that this subset T is a subspace of R2, the two-dimensional Euclidean space. So we make the following observation. Any vector in T can be written as a multiple of this vector 1, 0. So in particular, if you have a vector x0, you can write it as x as your scalar multiplied by the vector 1, 0. So this one vector alone is able to span that subspace. Any vector can be written as a multiple of this one vector. So this subspace is spanned by just one vector. And since it's only vector, a single vector is by definition considered to be an independent set. And it turns out that it spans T. So you can think of it as a basis for T because it's an independent set and also spans the vector subspace. And therefore, we can now say that's a basis for T. Since its basis has only one vector, we say the dimension of that subspace is 1. So I hope that makes sense. Again, we are using ideas that we covered in the previous class. So you must at all times try to go back and master the previous classes so that what follows makes sense. So we look at a second example. So we look at the subset of R2, which is defined as follows. You have the first vectors of this form. The first slot will just have some real number, and the second slot would be twice the real number in the first slot. So now any vector of this form is what you're looking at. Again, this is a subset of R2. We list some examples of vectors here, which are in S. So these are vectors whose y coordinate is twice the x coordinate. So
sorry, Daktari, your screen has not changed. It's still in the...
What are you seeing on the... Can you read the first?
The single vector 1, 0 forms a basis for T. This means the dimension of T is 1.
But from my side, it was okay, yeah? Daktari.
Then mine.
From
Mine
our
is
side is
okay.
okay.
Maybe he needs to exit and join again. I don't know. Is that okay?
Daktari had met some people in the lobby.
Just checked. There's nobody in the lobby. Whoever was there. There's only 22 people in the class, I think. I'm not seeing. So last time we agreed on a few things. One is if you're going to join the class, it's important that you have your full name appearing. So there are two people here. I don't know who they are. There's Renas and Ryan. I'm going to remove them from the class because I need to be able to identify them with their full names. So yes.
You can change.
Yes. Okay. If you don't change, we'll have to remove you. There's also Renus or Renas. I don't know how do you pronounce that. So Renus is not responding. We'll just remove them from the meeting. So he can always come back, but he just needs to put his full names there. Okay, I'll go back to the. I'm not seeing anybody. So Ryan is okay now. Renas has not changed his name, so. So I hope you can see the correct slide on your screen. So this one says consider the following subset of R2. So we have points in R2 which consist of this kind of vector where we have the first slot, the second slot being twice the first slot. That's all. Here are some examples of such vectors. So we want to see if this is indeed a vector space, subspace. So if you were to think of it graphically, again, this would just be points that lie on the line y is equal to 2x. The y coordinate is twice the x coordinate. And we know that this passes through the origin as well. So if we add any two vectors from here, so we have to pick two vectors. One is x1 and 2x1. The second vector is x2 and 2x2. So if you add them, we still get a vector on the same line because you can see the y coordinate is still twice the x coordinate. So that covers the first property that we need to check. The next one is what happens if you multiply any vector from that set by a scalar. Again, you still end up with a vector in the same set because our vectors, the only requirement is that the second slot will be twice the first slot. We still get that when we multiply by a scalar. So those two properties hold, and therefore we can conclude that this set, this subset of R2 is a subspace. So that's the conclusion we can make there. Now,
Doctor, I have a question.
Yes. Ask.
Previously, we discussed about linearly dependent points, vectors. And in your previous line, I've seen that you've noted that all of those vectors lie on y is equals to 2x. So while doing the while revising my notes, I noticed that linearly dependent vectors, when drawn on an xy plane, they are usually on passing through the origin. It's usually a straight line. Is it related to what you're saying on point number 3?
Cannot pass through the origin. Unless, what do you mean?
Like if you draw any linearly dependent line, especially in R2, if you
So
plot
we can't
any
have a
point,
linearly, we can't
any point,
have a linear.
okay, I meant points. If we plot them on an XY plane and then you join them through the origin, it usually becomes one line.
Yeah, that is true. If you have any two linearly dependent, any line through the origin will be a subspace. So
Okay.
what you need to understand about linear dependence is simple. If you have two vectors and one is a multiple of the other, then those vectors are linearly dependent.
So on this,
if that is always possible. If you have
on
more than
point
two,
3,
it means one can be written as a linear combination of remaining ones.
on point 3, we are noting that these are all points on the line y is equals to 2x, which passes through the origin. Are we also
It's true.
implicitly saying that they are linearly dependent because any line that passes through the origin and all the points lie on that line, they're usually linearly dependent?
So I think I'll leave that as an exercise to you. Can you show that any points that lie? It's exactly. We have actually proved it indirectly here. So you do it formally. Can you show that any points that lie on the line y, 2 points on the line y is equal to 2x will be linearly dependent? So you write it out and share with me your solution. Then I'll be able to see where you're coming from.
Okay.
Write it out fully and share the solution. You can do that later, not now. For now, the focus is to show that all these points, this subset of R2, they form a subspace. So if you add any 2 points on the line, you still get another point on the line. And that was the other thing. If you multiply any of the points on the line by a scalar, you still get another point on the same line. So we conclude it's a subspace. And then on top of that, we observe that any vector in this set can be written as a multiple of 1, 2. So 1, 2 is not the only vector you can use. You can also use any multiple of 1, 2 as a basis. Now this one vector spans the set S. And given that it's only one vector, by definition, we say it's linearly dependent. And therefore, we consider this vector, the set consisting of this vector, as a basis for our subspace because it spans the whole subspace. So those are 2 examples of subspaces. And when you're working in R2, any line that passes through the origin will be a subspace. Any points that lie on that line will form a subspace. I think there are people trying to join. Let's see. Good. So I think there are a few other people again who have joined and they don't have full names. I will point them out. There's someone called Christine K. I'm going to remove that one as well, unless they explain why the name is not full. Who else is name is not complete? There's another one called Barty Room W. Again, the name is not complete. I'll have to remove you. So again, none of them is responding. So I imagine they will respond now from outside. Okay. I'm just finishing that exercise, then we continue.
Doctor, I don't know why I cannot see your screen. I think I've left several times because I'm trying to resolve the issue, but not getting help.
I may not be able to do much from my end. Is anyone else with the same problem? Is anyone else who cannot see my screen?
No,
Or is there?
Daktari,
Yes.
I just think it could be a few issues, minor issues with the teams. There is also one of us who is claiming that is in the lobby. But since from your end you cannot see anybody in the lobby.
No, I've just admitted the ones who are in the lobby. The problem is you have different people joining at different times. Wanachelewa. Like now, there's nobody in the lobby. As soon as I join, it should show here. There were a few, I think there were about 4 of them. I admitted them, so I don't think there's anybody. I think there is another one again. This one was Christine, I think. Now we have the name. Okay, so I've returned them. Okay, so we continue. I believe now this makes sense. We have seen 2 examples of subspaces of the vector space R2. So given that the subspaces they're all one-dimensional, both that we looked at are one-dimensional, and any line through the origin will be a one-dimensional subspace of R2. One-dimensional because any line through the origin can be written as a multiple of just one point on any one point on the line. So so you can't get any other smaller subspace of R2. The only subspace of lower dimension is one-dimensional, because the dimension of R2 is 2. So subspaces must have a lower or equal dimension. And if it's equal dimension, then the subspace will just be the whole of R2. So we look at another example, but this time we consider, again, there's a typo here. This is supposed to be R3. No, this is just R. These are 2, X and Y are real numbers. So this squared should not be there. X and Y are real numbers. So here we consider a subset of R3 consisting of vectors that of this form, where the last slot must be 0. The first and second can be any real number, but the last slot must be 0. So this is definitely a subspace of R3. We check if it's, a subset. We check if it's a subspace by picking 2 vectors from the set and we add them. You can see we still get another vector in the same set. So addition of 2 vectors from this set gives us another vector in the same set. if you multiply a vector in the set by a scalar, you still get another vector in the same set, as you can see from this explanation. So again, this is a subspace of R3. This time we're working in R3. So we now observe the following, that if you pick any vector in our subspace, we call it P. It's possible to write it as a linear combination of these two vectors. So 1, 0, 0 and 0, 1, 0. So these two vectors form a basis for our subspace P because they are linearly independent and they span our subspace. So these form a basis for our subspace P. Now that the basis has exactly two vectors, we will say that P is a two-dimensional subspace of R3, or the three-dimensional Euclidean space. So here is another one. Here again, this is a subset of R3. It consists of vectors that take this form. So this is determined by two values. You have to have two parameters to be able to construct vectors in this space. So you need two numbers, and the first entry is the sum of the numbers. The second entry is twice the first number plus the second number, and the third entry is just the second number. So pick any two real numbers and construct a vector of this form. So again, this is a vector in R3. So an example of a vector in this space is if you take x and y to be 3, x to be 2 and y to be 3, you will get the, if you compute all these, you get this vector 5, 7, 3 as one of the vectors in the set K. So that's just an example to show one point in the vector. So our interest is to check if this is a subspace. So let's check. If you pick 2 points, so here is 1 point. Remember, any point requires 2 parameters to be constructed. So pick any 2 parameters, construct 1 point, pick a second set of parameters, construct another point, then add those 2 points, and you will observe that you still get another point in the set K. It still retains the format for K. So let's see if scalar multiplication will still give us a vector in the same set. Multiply any vector in the set K by a scalar, arbitrary scalar lambda. Again, you observe that you still end up with a vector in the same set. And therefore, we can conclude that K is again a subspace of R3. There's someone whose mic is on. It's Daniel Mwangi, I think, who is speaking. Okay, I'll disable the mic. So then we have confirmed that this set K is a subspace of R3. Now, if you pick any vector of this form, observe that it's possible to write it as a linear combination of these two vectors. So yet again, we've come up with another two-dimensional subspace of R3 because it's generated by it's spanned by two vectors, and these two vectors can easily be checked to be linearly independent. So this gives us a two-dimensional subspace of R3 because it can be spanned by two vectors, two linearly independent vectors. So the other thing you can state is the following. If you have any two linear independent vectors in R3, the set of all linear combinations of such of those two vectors will form a subspace of R3 and a two-dimensional subspace. So for that reason, it means if you pick any two linearly independent vectors in R3, you can actually construct a subspace of R3. So to illustrate that, we pick two vectors which are linearly independent. U and V, in this case, are linearly independent in R3. Now we can construct a span of these two vectors as follows. Just pick two scalars, X and Y. Get this linear combination of the two vectors U and V, and you end up with a vector of this form. So any vector in the span of U and V can be written in this form, where X and Y are just a pair of parameters you use. So you need to fix two parameters. Once you fix them and construct them like this, you'll have constructed a vector in the space that is spanned by U and V. So these two vectors U and V form a basis for this space. So the aim for this was to illustrate that anytime you have a pair of vectors, it's always possible to construct a subspace of R3 in this case, simply by listing all the linear combinations of the two vectors. So this gives us all the form of any linear combination of these two vectors U and V. So this is just stating the same. So the span of U and V will simply be the vectors that are of this form where X and Y is in R. So that completes the example. So in general, when working with R2, we saw that all one-dimensional subspaces are simply lines through the origin. When you come to R3, we also can observe that any two-dimensional subspace of R3 will be a plane that goes through the origin. So any subspace must contain the origin or the zero vector in that case. So in addition, if you pick any single vector in R3, get all multiples of that vector, you still are able to construct a subspace of R3 that is one-dimensional because it is spanned by just one vector. This means if you pick any non-zero vector from R3, then all multiples of that one vector form a subspace of R3. Are we together up to that point? So it's possible to generalize this to other vector spaces, but since most of our work will be around the n-dimensional Euclidean space, that's why I've limited my examples to this. And anything you can do in 3 dimensions, you can naturally extend it to any finite dimension. So to take that point further about the span of a set of vectors, if you have a finite subset or a finite set of vectors from a vector space, suppose we have exactly R vectors from a vector space. So let's, in this case, we'll insist that we are working in Rn. It can work, the definition is general, it can work for any other vector space, but To get a span, you simply get elements of the subspace by computing all linear combinations of the given R vectors. So if you get the set of all linear combinations of these vectors, V1, V2 to VR, you will get the span. You'll get a span of the set B, set of vectors B. Now if you add one more condition, now if it turns out that B is a linearly independent set, then that set becomes a basis for your subspace, right? If B is linearly dependent, again, not all is lost. We can still recover some honor out of this. You'll be able to, it will be possible to drop some vectors, and then you'll be left, eventually you'll be left with a linearly independent set that still spans that would still be the span B, or will still be in the span of B, sorry. Not spanning B, it will still be in the span of B. So I don't know if, let's see, do I have an example of this, or I need to go to the... So this again just repeats what we said. If you can find one-dimensional subsets or subspaces of R3, the one-dimensional subspaces are lines through the origin. We saw earlier that the two-dimensional subspaces of R3 are the planes through the origin. So, but if earlier on we also saw that the set with just the zero vector is a subspace. For this case, we define the dimension of the subspace containing only the zero vector to have dimension to be zero. The dimension is zero. Any other subspace will have dimension greater than zero, one or more. It has to, dimension must be an integer though. So this introduces a new concept called the dot product. But maybe before I don't know if any diagrams, the diagrams will be helpful. Let's see if I can try to illustrate some of the points before. If you have questions about what we have done, you may ask. So let's see if we can say some more. So we've made some statements that if you are in R, if you happen to be in R2, so this will be your x-axis, and this will be your y-axis. So our claim was the following, that if you have a point if you have a line going, any line going through the origin will be a line of the form y is equal to, today the mouse is misbehaving, y this, I need to get a pen. I think I'll do that. So this is what we get, y is equal to ax. That's what we get. Any line through the origin can be written like this. So if you want to describe a point in any vector that lies on that line, it will be a point of the form x, and then the second slot of that vector will be ax. Now you can show that any two such vectors, if added, will give you another vector of the same form. The same happens if you multiply by a scalar. you still get another vector of the same form. So it's just one dimensional. And we can, because it has one dimensional here, simply means it's one direction. You can think of it as being, you can only move in one direction, right? So and then, so this can work for any other line. Any line that goes through the origin will, as long as it contains the zero origin, the zero vector. My drawing is not very accurate, but assume that all those lines pass through the origin. These will all be one-dimensional vector spaces. So there are infinitely many one-dimensional vector spaces of R2. In R3, it's harder to draw. So R3, you need all these coordinates. So if you have a plane, so you'll assume that this plane passes through the origin. It's quite hard to draw. But in a plane, you can move in two directions. So usually you will need two vectors. If you have two vectors, you'll always, and any two vectors that are in different directions on the plane, the vectors must lie on the plane. You can use them to reconstruct any other point on the plane. So this is now two-dimensional because you can move in two directions in the plane. Again, you can also have lines. But now you need to have lines that pass through the origin. So this will simply be, if you have a vector that is in the same direction as that line, then any other vector on that line can be written as a multiple of this vector. So this gives you a one-dimensional subspace of R3 because you just need one vector to generate any other point on that line. So I hope that helps. So the other important concept that we need is a dot product. So if you have any two, let's start with the R2. If you're working in R2, then you can get a dot product of two vectors as follows. If you have two vectors, U and V, their dot product is simply, the dot product is represented by this dot. So you have the first vector x1, y1, x2, y2. The dot product is simply, you multiply the elements in the same position. So x1 and x2 are multiplied, and you also multiply the elements in the second slot, y1 and y2, and then you add them. So the resulting number, because the result will be a number, one number, is the value of the dot product of u and v. So we denote the dot product of u and v as u dot v. Does that make sense? So that's just, here is an example. That was the definition. You can apply it to any pair of vectors that you have. So I think this is self-explanatory. Simply multiply and add. Unless there's any question here. I think this is fairly self-explanatory. If you get u dot v, simply multiply 2 and 7 to get 14, 3 and 11 to get 33, and when you add them, you get 47. So it is one number. The dot product of any two vectors will result in a real number in this case. So there's a third vector, w, and the dot product of u and w is computed here. In this case, you get the dot product to be equal to 0. So it's possible for the dot product of two vectors to be 0. When it's 0, we say they are perpendicular. We might use that again later. So we do a general definition. In this case, we do it for R3. Again, the idea is the same. It's just extended to 3 slots. Multiply elements in the same slots, and then you add the result. Once you add those, you'll get one number. That number is the dot product of the 2 vectors. So it's important that you observe the dot product of 2 vectors will always be equal to a number. It will not be another vector. I usually see that confusion happen in exams. So that's why I'm mentioning it. For some of you, it's obvious. For others, it may not be. So this is a general case. If you work in the n-dimensional Euclidean space, pick any 2 vectors in Rn. The dot product will follow the same pattern. Simply multiply elements in the corresponding positions, get all those products, and then add the products. You'll get one number. So the next thing we'll look at is the magnitude of a vector. Magnitude is just the length. It's the length of a vector. So you can obtain it as we use these bars, these double bars on the side to denote the magnitude of a vector. So when you see those 2 double bars on the side of a vector, it means the magnitude of the vector. The magnitude of a vector can be obtained as getting the square root of the dot product of the vector with itself. So for example, if you have this vector 2, 7, its magnitude is simply the dot product, then you get the square root. So the magnitude of V is the square root of 53. So again, an example here, but in R3, the same idea, get the dot product of U with itself, and then get the square root. So this vector in R3 has a magnitude or a length of square root of 59. So if it happens that the vector has magnitude 1, we call it a unit vector. So any vector that has length 1 is called a unit vector. So anytime you have a vector, it's also possible to convert it into one of unit length. And you do that by multiplying it by 1 over its magnitude. So 1 over its magnitude will give you a scalar. If you multiply that scalar by V, you end up with a unit vector. So here is an example of anytime you have a vector and you want to convert it into a unit vector. It will not be the same vector, it will be a different vector, but it will be in the same direction with a magnitude of 1. So we do the same, get dot product of V with itself. Turns out to be the square root of 3. And if you want to write V, convert V into a unit vector, simply multiply it by 1 over its magnitude. So 1 over root 3 multiplied by this. So this conversion is useful when working with eigenvalues and eigenvectors. Sometimes you want to get, there's a process called orthogonalization. You will need this operation there. So for now, we're just making the building blocks. Like I said, you cannot apply what you don't know. For now, let's figure out what we need to know before we can apply it. So it's also possible to compute the distance between 2 vectors. So if you want to get the distance between the 2 vectors, simply get the difference between the 2 vectors and then compute the length of the resulting vector. So the difference, u minus v will be 1, -3. So once you get the difference, you can now get the magnitude of a resulting vector. That gives you the distance between the two vectors. But these are things you've already done. You know how to compute distance between 2 points in R2. We're just generalizing it now to larger spaces. So the same idea now you can extend to R3 or any arbitrary finite dimension. This can be done. You just get the difference between the two vectors. The resulting vector, you get the magnitude of that resulting vector, and the answer you get will be the distance between the two vectors, u and v. So this is symmetric. The order in which you do the subtraction is not important, because the distance, if you move from u to v or from v to u, it's the same distance. So the natural extension for this to larger spaces is the concept of norms, right? So what exactly is a norm? So a norm is basically some way of measuring the size of a vector. What we measured up there was an example of a norm. There are different types of norms, but the only norm that we shall be working with is this Euclidean norm. Which simply, again, the operation is you get the magnitude of the vector v as the square root of the dot product of v with itself. I think you're familiar with this summation notation from undergraduate work. So these other two norms, they also measure distance in some way, but we shall not be using these two. We'll focus on the Euclidean, just the normal distance, computing distance between 2 points that you know from your mathematics. That's the one we shall use. We might, this norm is used in some cases. When you're doing regularization, L1 regularization, you use this norm to measure distance. But we're not doing that in this class. I think you probably will learn that in I don't know, whoever new regularization for things like regression might cover that. So another special case, if you have a pair of vectors, we call them orthogonal if the dot product is 0. So this orthogonal is similar to the vectors having an angle of 90 degrees between them. So now it's possible to have a set that is orthogonal, or what we call an orthogonal set, and we'll have that if every pair of vectors that you pick turns out to be orthogonal. So these are also very important when working with the orthogonal decomposition of orthogonal eigen decomposition. We will need these ideas. So now again, let's make sure you catch the building blocks because we are going to be using this. So don't overlook them. Make sure this as unexciting as they may look, we're going to be using them. So it's important that at this point, your focus should be on mastering them. So that when we start using them, we don't have to go back again to define them. So these are two examples of vectors that are orthogonal. Their dot product is 0. This is basically the direct 1, 0 is in the direction, a vector in the direction of the x-axis, and 0, 1 is a vector in the direction of the y-axis. They are definitely perpendicular, and their dot product is 0. Here is another pair of vectors whose dot product is 0. Again, if you draw them in the what do you call them? If you draw these vectors in the plane, you will see that they are perpendicular. So again, here are more examples of orthogonal vectors, but in 3 dimensions. You have u and v, get the dot product is 0. Again, another example. This one I think is a repeater. We've already done this example of orthogonal vectors. So again, we are repeating this definition. We say if you have a set of 2 or more vectors, we'll say that it's an orthogonal set if every pair of vectors in the set is orthogonal. So in 2 dimensions, this is an example of an orthogonal set but there's only one pair anyway, and that pair is orthogonal. If you try to get the dot product of these 2 vectors, you will see that it is 0. And so this is an example of an orthogonal set in R2. If you move to R3, here is a set of vectors, and you can double check. I hope I didn't make any mistakes here. If you get the dot products of any pair of vectors in this set, that should equal 0. So they're mutually orthogonal. Any pair of vectors you pick will be orthogonal. So if in addition to being orthogonal, every vector has length 1, then we say that the set is orthonormal. So an orthonormal set is just a special case of an orthogonal set. The orthogonal set where each vector is of unit length. So if you just add that restriction that every vector must be of unit length for an orthogonal set, then we now call it an orthonormal set. Is that making sense? Today we have not taken a break, so but I believe hamjachoka. Am I right or am I right? Am I?
Right.
Yeah, it's important to hear people talking. Sometimes I might be talking to myself and I don't know. So you can have cases where the basis of a vector space consists entirely of orthogonal vectors, or is an orthogonal set. And in such a situation, we call it an orthogonal basis. We will also need this later. We'll see how to construct orthogonal bases. But it's basically a basis where the set of vectors in the basis form an orthogonal set. So the other one for that, again, the special case of an orthogonal basis is where every vector is of unit length. So this is a basis for R3. And if you can double check that the dot product of any 2 vectors here will be 0, and therefore the set is orthogonal. It also turns out to be a basis. This is a set of linearly independent vectors. There are 3 of them in R3, and any 3 linearly independent set of vectors, any 3 vectors in R3 that are linearly independent form a basis for R3. Because the dimension of R3 is 3, so that is guaranteed. So the reason for bothering with orthonormal basis is because anytime you want to compute coordinates of a vector within the space, with respect to an orthonormal basis, it's quite easy. It's very convenient. We will, and I don't know if I have an example of this after that, where we, yes, here's an example. So if you want to write this vector W as a linear combination of the vectors in the basis B, where the basis B consists of orthonormal vectors, then you can find the coefficients quite easily by computing just dot products. So if I want to, the aim is this. Let me write, we have W. I want to write W as a linear combination of these vectors. So I'll pick a scalar alpha 1, U1 plus alpha 2. And then you can see what I'm writing. As
Yes.
alpha 3, U3. So that is W, this vector. We want to write it like this. So the question is, how do we find these coefficients? Alpha 1, alpha 2, alpha 3. One way to find them is to solve some system of equations, three equations in 3 variables, but we don't want to do that now. And we shouldn't anyway, because it will be hard work. So the question is, how do I find alpha 1? So remember, keep in mind that these vectors are they are of unit length and that they're also orthogonal, so they form an orthonormal basis. So how do I find these coefficients? It's simply by getting dot product. So if I want to get alpha 1, it will, that will be the first coordinate. It will simply be the dot product of W with U1, which is 1 over root 2. You can double check that. I hope they are correct. Then there's W with U2 to get alpha 2, which turns out to be 0. Then W with U3 to get 9 over root 6. And that gives you the alpha 3. So I can quickly get the coordinates of W with respect to this orthonormal basis by just computing the these dot products. That's all. So that's the advantage of working with the orthonormal basis. So this Gram-Schmidt algorithm is a process of converting any set of linearly independent vectors into an orthogonal set. It has a lot of, I don't know if I should do this. Maybe this is best done in a fresh class. It's extremely, has a lot of detail. Starting this in the middle of a class will be tiring. We will not even finish. But essentially, it's a process of obtaining, anytime you have a linearly independent set, sometimes you can always convert it into an orthogonal, or even orthogonal set if you want. Most of the time, the target is to make it orthonormal. It's always possible. And this algorithm gives you a way to do that. When you're working in the computer, it's done behind the scenes. You don't need to do it manually. But doing at least one example by hand will be helpful for you to understand what's going on behind the scenes. And for those who are interested in research, it's necessary. You can't escape this mathematics if you're interested in research. And since the course is a data science course, it assumes you plan to do research. So it's necessary for that you are familiar with these foundational concepts. So this Gram-Schmidt algorithm, I propose that we do it as at the beginning of a class, not after you have done a lot of calculations, when we have a reasonable amount of time to complete it. I can see there's some formatting that needs to be done here. Some lines are going over the. So I don't know, we could start. Matrices is a good topic to, if you wish, we can start on matrices, or we can end the class there. I'm also tired. I've been talking for most of the day. I just came back from a full day camp. We are running a camp to select the Kenya team for the International Mathematical Olympiad. So we are teaching some high school students at semester, and I've been there the whole day. But if you are also not tired, we can do some matrices before we close. I need some feedback.
Let's start on the next class.
Pardon?
Let's start on the next class.
The sound is breaking. I can't hear. Who is speaking?
We start on the next class.
So we close today's class.
Yes.
Okay,
Yes.
so I think that is a free and fair election. We can stop there, I think. Is that okay? Then, unless there are any questions, if someone has a question that's burning and they need it answered now, we can do that. So I'll stop recording. So the class is